Good morning, everybody. It's a good to be here with you this morning. As mentioned, I'm Sam Fuller. I work at a startup company called FlexLogix. I'll tell a little bit about it over the next 30 minutes or so. But I really want to talk about the kind of the evolution of this new form of processing and what it takes. If we look back in time to back in the 60s, there was we had computers back then. And there's this story about at MIT where there was Marvin Minsky was a researcher at the time, hired an undergraduate to spend the summer linking a camera to the computer, right, and then getting the computer to describe what it saw. Now, I can think about this and recognize that that wasn't an unreasonable thing, right? I mean, camera was going to be black and white, probably pretty low resolution. You could point it at something. You could write a program to kind of look at the lines and look at the structures and probably say what you saw. But unfortunately, they didn't make the deadline, and it turned out that was a much harder problem than we thought it would be some 50 years ago. And after that time, obviously, we've gone through several hype cycles, inflated hypes and hopes, and then winters associated with that. I was in grad school in the 80s, and I can remember working in studying computer vision at the time and neural networks. I don't think we were calling it deep learning, but definitely we were talking about neural networks. We were combining convolutions with various transforms to simplify images. And at the time, they weren't deep networks, but most networks were described, 3 layers, 4 layers, 5 layers or so. And you might have a few hundred neurons involved in that processing. And then kind of as we moved into the later 80s, we had what I refer to as the attack of the killer micros, right? So we started building more and more complex general purpose processing onto smaller and smaller silicons. The personal computer revolution occurred, and it just got so we were focused a lot more on data processing and connectivity, and not so much on what we would now call AI and other things. It was always there, but man, there was a whole lot more money to be made elsewhere, and that's where all the money went. And then more recently, in the last 10 years, the explosion of data and the ability to kind of compute at a scale we hadn't been at before has now caused this new renaissance in AI processing, and now we worry not about can we do it, but the ethical implications of what it is we're trying to do with this technology. Obviously the AlexNet now 10 years ago kind of changed the game, but what it really did was talk about both massive data in terms of training a large network and the need for significant computational capacity to actually do this work. 10 years ago, 1 billion transactions was still a lot of work, right? It was a lot of processing to do 1 billion operations, and especially if you're trying to do something in real time in a fraction of a second. But it set a new path, and since that time, obviously the complexity of these models has continued to grow, as well as the sophistication of the algorithms and the technology, the data sets. I know a lot of folks here are studying or working on how do you generate the data to train these models and do these things. So as we've done all that, now we're at a point where now we actually can use this technology to deploy it. We were just had some great talks on retail and mapping type applications where this kind of work is now becoming very routine, right? You can do retail counting or even checkout in retail environments. The industrial use of the technology is now evolving beyond traditional algorithmic computer vision to leveraging trained networks for doing things like defect detection and other things like that. Obviously, the medical imaging space, we're getting much better at replicating the expertise of radiologists. I think we need to remember radiologists themselves need about a decade of training to get to where they are. And we can't expect this technology to get there in a year or two. It's going to take time, but it is happening. And we're able to, once that is trained, once we've developed that, the key thing is that it's very easy to replicate. It's a lot harder to grow another radiologist. That takes decades. Once you've got the algorithms right and you can leverage, and you have this technology because it's digital, because it's based on these kind of mathematical concepts, it's very easy and very inexpensive to replicate. And then there's just kind of normal things, like dressing rooms, other type of medical things where we're able to use this technology, which I say is still fairly primitive, but is useful now. So lots of evolution of technology in the last decade along this realm. So now when we think about the tough new problems related to this, and I've been, like I said, I was in grad school in the 80s. I've participated in a lot of the general purpose processing roadmap development. In terms of CPU technology, even multiprocessing technology, I'd say those are mostly solved problems. I don't know that there's a whole lot more. I mean, obviously there's continual innovation and enhancement. The big problem is always memory bandwidth at this point. We have plenty of computational capacity. It's how do you keep these machines fed? Operating systems in the open source movement, fairly strong. Lots of computing boxes, the mechanicals, the cooling technology, the network connectivity, the overall software paradigms, and the imaging sensors, the vision sensors, the cameras, those things, they all exist and are really robust competitive markets. And so I'd say those problems are for the most part solved. It's not that there won't be continued innovation, but those technologies all exist. But the tough new problems, especially related to computer vision, one is the software complexity. How do you represent a program that's performing 1 trillion operations, because that's really at the level we are to do this stuff. It's not C++ anymore, right? It's not C, it's not those things, right? We have to have new paradigms of software to support that. And then we need to talk about efficiency. How do you fit that, right? Because ultimately, these technologies need to fit in small spaces. They need to be able to fit in our pockets, maybe on our heads, maybe, but if not that, in the ceiling, elsewhere, at the edge. When we talk about that, at the edge, I mean, we can put kind of infinite capacity in the cloud, but there are real reasons. Sometimes they're bandwidth, sometimes they're cost, sometimes they're privacy, where we want to actually do the processing. Latency. We want to do the processing at the edge. And so the question is, how do you do those things? So I'm going to talk a little bit about both of those, but probably more on the efficiency piece, because that's what I'm trying to represent. Okay, so the first thing is to try to get a handle on when we talk about teraops. One of the things I note about computing technology today is it's almost magical, right? Anything we can imagine, we can probably produce visually. But the reality is there's a lot of hard work that goes into the processing. So if we think about mega, giga, tera, right? I built this slide to try to convey the challenge that the engineers, hardware engineers and others face. In that, the evolution that we've had of computing technology to get from kind of megahertz machines to gigahertz machines, we can understand that fairly well. We're not going to have terahertz machines, right? The CPUs will not go to terahertz speeds. So that the paradigms that we've used won't get there. And if you look at this and you think, a megasecond is 12 days, a gigasecond's 32 years, but a terasecond's like 32,000 years, give yourself a view that it's not, if I'm not going to get my frequency up, I've got to exploit some other technologies. I've got to have new paradigms of processing to solve these problems. We can kind of do some of it, but and in fact, we can get into kind of the tens of gigaseconds reasonably well with existing technologies, but that last 100x to get to kind of teraops processing is just not going to be solved with the techniques that we've used in the past. We need new techniques. And it's important that we continue to increase the computational capacity, because what we've learned is that the more computation you do, the more accurate your results will be. I think we're also learning that there's no little silver bullet, there's no like hidden dimension that we can exploit that transforms everything into a problem that can be solved with current technologies. So we've got to be able to continue to push the throughput, the computational throughput. That'll increase the accuracy, that'll increase the overall capacity of the vision systems that we're developing. When we look at these models, this is essentially another view of that. The accuracy, these are a set of YOLO V5 models. The accuracy of these from small to medium to large, right? There's just kind of a continual MAP improvement as we increase the computational capability, but between the small and the and the larger, especially the extra large, there's like a 10-fold increase in processing, gigaflops, parameters, and such. So we, as we look at this, we're looking at what we can do now, and for our accelerator on a YOLO V5 small model, we do about 70 frames a second. But when we get to an extra large model, that's about 10 frames a second. And it's all due to the, kind of the overall complexity, the amount of processing that you have to do. Those things are going to continue to push, and our expectation is that we're going to have to be kind of beyond Moore's law capable in terms of bringing more computational capacity, because we expect the models will continue to grow in complexity, that people will use the model that they can afford to use that achieves the accuracy that they're targeted at, that was talked about earlier. Okay, how are we doing time-wise? The other thing to recognize is that these models are evolving, so the flexibility is key. So back to the YOLO V5, which we find is a really capable model in terms of accurately performing object detection. There have been, in the last, year and a half, 6 different releases of that where they've continued to incrementally improve the technology. And these are, relative to the larger steps of, YOLO V3 to YOLO 4 or 5. I guess I understand the different heritages of those. But even within the YOLO V5 subvariants, there's continual innovation on activation functions and on the different sizes and flavors that are supported, that you really can't build an ASIC, and it's not a good idea to try to build something that's an ASIC that just solves this one problem, because it's going to change, and they're changing fairly rapidly, and so you need that flexibility. So now that we know we've got a really high performance processing problem to be able to help a computer see, to perceive visually, what are the various approaches to take? So one approach, obviously, is that you can do a lot of this in the cloud. I actually copied this directly from the AWS machine learning, their elastic inference pricing. So their view on deep learning inference to analyze a single video stream, using an extra large instance of EC2, and then an accelerator as well, a medium inference, you're looking at, I guess, 17 cents an hour plus 12 cents an hour for the accelerator. So 29 cents an hour to do that processing in the cloud. If you do the simple math, it's, a little over $200 a month, over $2,500 a year. So if it really is something that you're kind of continuously streaming and you want to be able to process that in the cloud, that quickly becomes pretty expensive. For development purposes, no problem at all. I think it makes a lot of sense to do a lot of this development work in cloud environments, but as you go to deployment, large-scale deployments, then you really have to think, is the cloud the right place to host my Edge AI, my vision workloads? Because of the cost. They don't charge you anything to move data to the cloud, which I guess is a good thing, but if you try to get results back or move data around within it, then you pay for that. So a lot of folks will, you can take the GPU out of the cloud, put it in the edge, and that's the primary way I think everybody looks at this problem right now. It's, GPUs are good for inferencing, training especially. They've got tons of memory bandwidth. They're just built around memory bandwidth. They can support the N8s, 16s, 32s, floating point, all the precisions, data types, and a really fairly strong software ecosystem. But they are large, and a lot of the, so they're built on fairly large pieces of silicon, and those large pieces of silicon generate heat when they process. And they're more expensive because you don't get as many of them per wafer, and they got fairly complex packaging. And they're power hungry, so they have to put big fans on it, and they take up 2 slots, 3 slots of space. It's pretty easy to get started using GPUs, but it gets hard to optimize for because you're really dependent on the model. You're really dependent on the libraries and the kind of the regular release of libraries, because everything is really hand-coded and optimized in those libraries to use them. And unless you're a really large customer, it can be difficult to get support, and I understand it's pretty hard to get, to even buy boards now. Like that, we're always running into customers who are like, they just, they built something and they can't get the supply they need out of the supply chain. But I think GPUs have provided a tremendous service to the industry in providing a capable computing platform, a parallel processing and capabilities to kind of get us to the point where we could demonstrate and prove these capabilities. So we'll go a little bit of a commercial now. The company I represent developed an accelerator technology that is similar in performance to an ASIC, but is really dynamic to new models. So it's not fixed hard logic. Now, our company has a heritage in FPGA technology, but this is not an FPGA. We call it it's an inference accelerator. It uses a dynamic tensor processor array, so essentially sets of tensor, one-dimensional tensor arrays that we're able to reconfigure very rapidly to map to the various layers within a machine learning model. And so what that drives is a very high level of silicon efficiency and a very low level of power and performance. And so really designed around the inference problem, not the model development or training problem, but the inference problem. How do I get a very efficient, low-cost solution for broad-scale deployment of vision at the edge? So if I compare the comparison on the GPU-based solution to what we're offering, GPUs obviously have lots of Macs, up to 10 or 20,000 max in some of the newer, bigger ones. We're about 4,000 max in our design, but we're very, very efficient in how we use them. The computation are predominantly via DDR. So the pipeline of the GPU is designed around running out of memory as opposed to running out of kind of local cache. Whereas our design is really designed on running out of local memory. There's kind of L2 cache on chip. There's a DDR that you in the background use to refill stuff, but you're designed to run around something that's right there, and that simplifies the design significantly. So from a software perspective, I don't think I've got a slide in here that describes it, so I want to talk about it right now. The way we look at this whole kind of machine learning paradigm is that technologies like PyTorch, TensorFlow, and others kind of create the programming, create the model, and you don't program our device with those technologies. What we do is take a trained ONNX model. So you develop your model, you train it, you get it to the level that you're really comfortable with, and then you're able to take that, export it as a trained ONNX model, and then we're able to take that and convert that into the executable that runs on our device. So you don't program our device specifically. You are taking something that you developed you can develop in the cloud, but when you're ready to deploy it in volume, then you make this conversion and then you run on our device. And so, you can update that at any time that you want to, but fundamentally, it doesn't offer a different programming model than what you should be working with now. Obviously, much lower power, much more flexibility, and designed for efficient processing at the edge. So when you look at that versus like the Tesla T4, it's about 1/10 the die size. So there's a lot of efficiency there. And then depending on the workloads, I won't say that all workloads will see this, but we see some customer workloads that we're able to run at 2x the performance of a very large Tesla machine. And a lot of that is just the inherent efficiencies of the processing that we bring. So that kind of brings us to this concept of having something that provides that high level of the performance that you would expect to get from an ASIC or a custom piece of logic. Oftentimes you think about like MPEG or H.264 video decode, right? You essentially design something that's really good for that, and it's super low power, super efficient for that. But the problem is that when the VP9, some other algorithm comes, it just doesn't match well. It doesn't do it well. So you need something that has both that efficiency and performance, but has the flexibility of software that can be kind of reconfigured as needed to support new workloads as they appear. So that's really what we've tried to design, and then that enables these kind of low power, low cost form factors. So ultimately, our targets are the industrial, kind of retail, agriculture areas where, we've built an infrastructure that's designed. A lot of the infrastructure is designed about how do I get power out of the system? How do I get the heat and power? Because I've got fairly, I'm either using CPUs or GPUs that are inherently inefficient and generate a lot of power to do a certain amount of computation. And so what we want to do is reduce that down into something that's very efficient at that particular set of computation, that teraflop that you need. I mean, you still kind of have the gigaflop machines around that are loading your files and drawing your screens and doing all of that work. But taking a complex machine learning model and taking the bulk of the mathematic offload out of a CPU into a structure that's real optimized for it is important. And it really is a paradigm shift that I think we all have to realize. We cannot continue to expect that the machines we develop on are the machines that we will deploy on. If there's nothing else that you can take away from this, is recognizing that we need to have these technologies like ONNX that are able to separate the development phase from the deployment phase. And if we do that, I think we're able to both grow the richness of the development side and also enable us to optimize and develop much more efficient, cost-effective, lower power, more capable or higher performance solutions for the deployment of inferencing. So just I kind of wrapped it up already, but we can do this now. This is something that 10 years ago we really couldn't do. We know how to do it. We know the technology, and it's really computationally intensive and will continue to be so. There are new architectures required to solve this. The traditional approaches we've taken will not be sufficient. And as I mentioned, the optimization points, training and inference are different. You can cost effectively accelerate standard computing systems with these kinds of accelerator technologies. So I hope that that you can take that away, that these should be here, and we should all be looking and considering using and exploring the use of dedicated accelerators for the inference tasks. Thank you so much for your time. I appreciate it.
Thank you. Great presentation.
Yeah.
So we have some questions. Have time. 3 minutes.
Yeah.
Any questions from here? Because I have my own questions. Dr. Alimo.
Thank you so much for your great talk. In fact, it's very interesting area to work on. And based on my experience, these hardware can handle certain type of machine learning techniques. And I did lots of experiments, and I understood that many of them are designed for maybe convolutional networks. However, we see that we have multi-layer perceptrons, we have graph neural networks. So is your system or hardware capable of handling different architecture? And the second part of the question is the ONNX that you have, is it specific to your own model, or is it using specific platform?
A platform. Okay. So the great questions. It is the case that there can be a lot of complexity in a neural network model. One of the things that we often talk about is that if the people who are writing the models understood the capabilities of the hardware, they write them differently. It's not that you need to target it, but that, for example, there are certain levels of parallelism, like the number of channels that are in a layer, that can be exploited pretty well with good accelerators. And if you try to map the algorithm to the natural channel bandwidth of an accelerator, you'll have more efficiency by doing that. But we have tried, and I'd say, at our first cut, we've got a lot of flexibility. Future iterations of the architecture will increase that. But things like transformers. So a lot of people are talking about transformers as kind of a head or a second stage, and there's some architectures that are like transformers all the way down. Those do map reasonably well to our architecture. We do make some assumptions in our architecture about the layering, the fact that you will have multiple layers and you will pass data via an activation function from layer to layer. We take advantage of that because we actually are reusing the same hardware between layers. And if you had a machine learning architecture that really didn't have that paradigm, or that maybe kind of split lots of things up, and we can handle some level of kind of skip connections or residual network things, but if like it had like 50 different residual passes, we'd probably have trouble processing something like that. But the current sets of models that we were aware of as we developed the technology are reasonably well supported by that architecture. But it is the case that accelerators, and it's also the case that like a GPU approach, there are inherent limitations in what a GPU can do because of the way it's architected. But there's a great deal of efficiency that can come if you understand what the hardware wants to do. Then you can really take advantage of it and get some very good efficiency performance. Thank you.
One more question?
One more question?
One more.
Hi, very good presentation. As a computer vision neophyte, I just want to ask you, do you happen to know if the transformer-based systems, do they use both the encoder component and the decoder component of the transformer architecture?
Well, both of those, yeah. Those piece phases of the transformer are needed to kind of complete the work, right?
Okay, I'm just saying because things like BERT use only the encoder, some use the other. It's all different combinations.
Okay. Yeah, on the vision stuff that I've reviewed thus far, it's both ends of it.
Thank you.
Yeah, and we do have, we set up a reasonable sized booth and demos for our break, which is coming up. So if you have other questions, we'd be happy to
All right.
have you, kind of show you.
Really appreciate it. Thank you so much.
Thank you.